Hello everyone, welcome in this video tutorial on treatment of merohedral twinning, generation of twin law and structure refinement. The program used are XPREP for the generation of .ins file, OLEX2 and SHELXL for the crystal structure solution and the refinement purpose. All these programs are available free of charge for the academic user. The necessary files required for the refinement are used with permission from these two gentlemen, Dr. Peter Muller and from Mr. Edlund, and the more detail about the present structure is available in this book reference, Crystal Structure Refinement, a Crystallographer's Guide to SHELXL. This is a very nice book edited by Professor Peter Muller. First of all, what is merohedral twinning? In merohedral twinning, the twin law is a symmetry operator of the crystal system and not of the point group of the crystal. The reciprocal lattices of the different twin domains superimpose exactly and the twinning is not directly detectable from the reflection pattern. Then what are the types? First is racemic twin and second is other merohedral twin. I am going to discuss today the second type. The twin operator belongs to the crystal's class but not to the Lave group of the crystal. This type is possible in higher symmetry crystal system like trigonal, tetragonal, hexagonal and cubic. This type of twinning can have drastic influences on the relative intensities of the diffraction pattern and may cause severe problem. Suppose this is the diffraction pattern or reciprocal space of the component number 1 and this is for the component number 2, then the overall pattern will look like this, fully overlapped diffraction pattern. So this type of twinning cannot be handled during the data reduction or integration. We can handle such type of twinning during the crystal structure solution and the refinement. Then structure solution. The structure solution in this particular problem will involve the following steps. The first step is generation of the .instruction file. Second step is structure solution and refinement by SHELXS and SHELXL in OLEX2. Third step is generation of twin matrix or twin law using XPREP, and the final step is structure or solution by twin refinement. So let's start the tutorial part. Okay, so this is the only file, the .skl file I have named merohedral.skl, and the first three columns are HKL, fourth column is I intensity and the fifth column is sigma I. Okay, so this is the standard format for the .skl file. I will close it and I will open this file in some program like SHELXL and I will go to project, then new, and I will give the name merohedral, and the file I placed in a folder on the desktop named merohedral. I will open this folder and I will find this file .skl file. Okay, I will select open and then I will go to the second option XPREP. I will press it and a window will open up. It will ask for the cell parameter. I have the cell parameter ABC and alpha beta gamma. A is 12.623, B is 12.623, C is 26.325, alpha is 90 degree, beta is 90 degree and gamma is 120 degree. And then I will press enter. It will select the lattice P. Okay, I will go with the program and enter. Then it will ask for the height symmetry. Okay, press enter and you will find the cell and it will select the option A. Hexagonal P lattice with R system value 0.067, which is looking nice. So I will select the option A as suggested by the program and enter. Then it will ask for the determine or input space group, enter, then press enter and then again enter and then enter. OK. And now from the systematic absence values here, the two possible space groups tested are P31 and P32. The R values are looking good and the program suggests the select option B. Okay, here I will go with the program and I will press enter. Okay, then again enter, continue it, okay, okay, and now it will ask for the expected molecular formula or some element. I don't know exactly the molecular formula, but I am expecting some osmium complex with triphenyl phosphine ligand and some chlorine ligand. So one element present is osmium, then chlorine, phosphorus, oxygen, carbon, and hydrogen. This is the only information I have. I press enter and then it will select option E, enter, then continue, and it will write the file merohedral. Named merohedral, I will press enter. Okay, and this is the file written in space group P32, and these are the cell parameters, and I will press enter. Okay, and okay. So now I have .ins file in the folder. So earlier I have only .SQL file. Now I have .ins file, the PCF file and PRP file. PRP file is the information present in here. So this is the information which is generated by XPREP. It is present in the .PRP file. Okay. So now I need these two files, .ins file and the .HKL file. Now I am going to solve the structure by some crystallography program. Here I am using the OLEX2. Okay. I will open up the OLEX2. This is the interface of OLEX2. I will go to the file, open, and then go to the required folder merohedral, open, and then I will open the ins file, open. So now I have to solve the structure. For this I will press this button work and then I will press this little inverted arrow and I have a number of programs for the structure solution. Since this structure has some heavy atom and a number of light atom, so I will select the program SHELXS and I will use the Patterson method. SHELXS and Patterson method and I will press the button solve. So what I get is some kind of structure. Here this is osmium and there are certain ligand, either they are chlorine or phosphorus. Okay, so I will go with the refinement. Here refinement program I am using SHELXL. I am using some cycles for 10 cycles and number of peaks 20 for now, and I will select the option ECTA to generate the zip file and I will press refine. Okay, so some atoms are getting bigger in size, so I have to delete them. Okay, Just select them and delete them. Then again go to refine. Okay, so I am applying the weighting scheme and refine again. The R factor is around 24% and the maximum peak is some 8.7 electron. So here I am using the peaks 79. Okay, the 50 peaks are enough. So let's decrease to view the difference Fourier map in a better way. So 50 peaks are enough. Okay, then I'm going to refine. Okay, if I compact it by pressing this button, okay, then I assume $200 cube. It will increase the size of the cube peaks for a better visualization. Okay, so 50 peaks, cube peaks are there. Then I'm going to refine. Okay, so I will compact, but I am not getting any benzene ring here, and there is no improvement in the R factor. The highest electron density peak is here, and this doesn't make any sense. So from here, I can't go forward in this refinement. So now I have to check for the twinning, and I have to apply the twin law for the further structure solution. For that, what I have to do, go back to the XPREP. Okay, go to the XPREP. It will ask for the parameter. Okay, put them 12.623, 12.623, and 26.325, 26.325, and then 90, 90, and 120. Press enter. Okay, again press enter. Now what I have to do, I will select the option M instead of option H. What is M? Here it is M, test for merohedral twinning. Okay, I will press M. Enter. Okay, again enter. Then enter. Now, if you compare the true and apparent Lave group, you will find that for the 3 bar and 3 bar 1M, the RINT values are 0.067 and 0.335. For the second option, for the Lave group 3 bar and 3 bar M1, the RINT values are 0.067 and 0.124. For the third option, the value is high. For the fourth option, it is high value and high value and high value. So you can see the only second option is giving us a reasonable value of R. So I will select this twin law. This twin law is 0, 1, 0, 1, 0, 0, 0, 0, minus 1. Note down this twin law and write this twin law in the .ins file with some batch scale factor. So 0, 1, 0, 1, 0, 0, and 0, 0, minus 1. Okay, so I am going to close this and I will open the OLEX2 and type here edit. It will open the .ins file and I will write here twin. What was that? 0, 1, 0, 1, 0, 0, and 0, 0, minus 1, and some base scale factor BASF. Let's start with 0.3. So here note down the R value is 24%. Now save it and refine. Okay, now you can see the R factor is down from 24 to 12%. That's good. And if you look at the difference Fourier map Now you can easily recognize some benzene ring. These are looking nice benzene ring. So I will select this benzene ring by using the shift key and arrow, left arrow, and I will make them carbon. So this ring is visible very nicely. Okay, there is one more ring which is looking nice. This one I will select these 6 cubics and name them carbon. Okay, and then there is no more ring is visible. Okay, no problem. So this should be phosphorus. Yes, this should be phosphorus. Any one out of these two phosphorus should be chlorine. Okay, that will be found by using the bond length. No problem. Okay, refine. Good. R factor is improved from to 11% some. Now, if I closely look at the electron density map, okay, press this button. Okay, let's see for some other benzene ring. Oh yes, here it is visible very nicely. 1, 2, 3, 4, 5 and 6. Name them carbon. Good. Yes, there is any other ring. Okay, just refine for now. Do it step by step and you will find the next ring in the next refinement cycle. Now you can see one more ring is visible. Select it and name all the atom as all the cubic as carbon. Okay, nice. Refine it. Now you can see the maximum cubics is around some 4 electron. Earlier it was 8 electron and the R factor dropped down to 10% from 24%. Now if you look at the difference map, now you can see one more ring is visible here. Select it, name it carbon. Okay, very nice. And there is some more ring is visible here. Select the 6 cubics, name them carbon and refine. Do it step by step, carefully. Okay, the R factor is further down. Now, how many rings are visible? There are 6 visible. Still we are missing 3. Okay, press this button and now you will see another ring here. Select these 6 cubics and make carbon. Now there is one more ring visible here. Yes, here it is. These 6 cubics. These 6. Make them carbon. Okay, so there are 3 rings. There are 3 rings and 1 ring is still missing. Okay, first do the refinement. Okay, so further R factor is dropped to 7.82%. Press this compact button. Okay, yes, one more ring is visible. Just decrease the cubic intensity and you will nicely see that ring. Okay, now, okay, yes, 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 now it is visible. 1, 2, 3, 4, 5, 6. Make them carbon and refine. Okay, so what I have to do now, there is some cubic very close to the osmium atom. So how to tackle this? Just select osmium and refine it anisotropically. Good. The maximum peak intensity is around 2.2. So here if you look, here it is Q1, here it is Q2, the two maximum intensity are here. So this is CO, carbon monoxide. So make it carbon and this one as oxygen. Now this is CO and this should be chlorine. Okay. Now refine, and there is further improvement in the model and in the R factor. Good. Now just put off the cupids, and now you can see some rings are good but some rings are not looking happy. Okay, make them happy. This one is okay. Now type FX66 and this ring will appear nice. Enter and refine. Now you can see this ring is looking good. Yes, now it is looking good. Then next, any other ring. Okay, other rings. Okay, this ring is not looking very happy. Select it, upward key and enter, and it will fix this problem. Okay, now this ring is also looking very nice. Go for some other ring. Yes, this ring also not looking nice. Upward key and enter and refine. Okay, now you can see all the rings are looking very nice. Okay, yes, this one, yes, this ring is also deviating from the flat symmetry. Select it and affix 66 and refine. Okay, now you can see all the rings are almost behaving very nicely. This ring, okay, select this also, affix 66 and refine. Okay, now you can see each phenyl ring is now looking very nice. Okay, this ring is also not behaving very nicely. Select it, affix 66 and refine. As this is a twin data, so we can expect some type of distortion in the benzene ring, but there is no need to worry, we can fix them. Now I can refine the whole structure as anisotropically. For this I will put the Q values here again and I will press anis, then regu, okay, then H add and then refine. Okay, now the R factor is further down, but one atom is NPD. Don't worry, select these two atoms and type EADP and refine. Okay. Now the all carbon atoms are looking nice. The maximum Q-pix is around 1.3. And this is due to some disordered ethanol molecule in the lattice. I am not going to model the disordered part. I am not going to model the disordered solvent in the lattice, otherwise the length of the video will become too large. I am going for some refinement, 1 or 2 cycle, so the shift gets stabilized. Yes, it is stabilized, but there is a warning. Structure may be an inversion twin. Okay, so how to get rid of this problem? Just go to INS file, type edit, enter, and make one as -1 and -1 as 1. This 2 is for it means that there are 2 twin components. And the base scale factor is fine to 0.394. So one domain is 39% and the other domain is around, okay, how much percent? It is 61%. Okay, so now save it and refine. So now you can see there is no more warning regarding this, and the space group is changed from P32 to P31. So P31 is actually the right space group. If I go for the formula, I will correct the formula. The Z dash is, I think, 1. So Z is 3. Now the formula is looking good. So I'll find one more time. So this weighing scheme will become green and the shift will get stabilized. Now everything seems to be nice. Goodness of fit is nice. The completeness is very nice. Find one more time. One more time. Now everything seems to be good. And there is maximum electron density is 1.3 electron, and this is due to some disordered ethanol molecule in the lattice. I am not going to model this one, but just I will find one or more time. So the shift will become 0 or almost 0. Okay, there's some extension. Fine. Okay, so there is no extension. No extension. Okay, now everything seems to be good. So here I am going to close the tutorial. If you have any question regarding the tutorial, you are welcome, and thanks for watching the video.